All right, this is Mrs. Query, and this is our last lecture on two-dimensional motion. And what I'm doing actually is really not out of the book, but some of my opinion, some of the most important concepts related to two-dimensional motion. So I have a projectile here, and this is launched at the ground level and lands at the ground level and reaches some dimension in maximum dimension in the y direction as seen by here. And it will land some delta x distance away from where it started from. So let's assume, just for chagrins, that it's launched with a velocity, we're told, that's 30 meters per second at 30 degrees above the horizontal. Notice there's my velocity vector. So I draw 30 meters per second, a line that represents that at an angle of 30 degrees above the horizontal. I want to the first thing I want to do is sketch the horizontal and vertical velocity, okay, and the acceleration vectors throughout the entire time it's in flight. So what do I mean by that? So this initial velocity, here's my initial velocity. It has two vectors, right? It has two components to it. It has an x component, so there's the vx initial, and then it has the vy initial. Okay, so I'm going to go through every single one of these dots, and I'm going to draw and if you can, this is what I want you to be able to do, to explain it. Tell me what's going on. Well, let's start with the initial. So I know that that velocity vector, which we're given at some value, at some angle, I can come along and draw, that's not to scale, so let's see if I can do that to scale. I can draw its vxi, and it's the reflection of that original velocity vector in the x direction, right? That's positive based on that. All right, so what about the y? Same thing. It's got an initial velocity in the y direction. Let's see if we can, velocity initial in the y direction, okay? And it's the component of that original vector, okay? Now, what is going on at b? Let's think about what's going on at b. What do we know about the acceleration? Well, we know that acceleration in the x direction is 0, and we know that the acceleration in the y direction is negative g. So let's think about the x direction first. If acceleration in the x direction is 0, what's happening to our velocity in the x direction? Isn't changing. So I can draw that velocity vector the exact same length. I'll call it the velocity x. It's the same as the original velocity when it was launched in the x direction, that is. Okay, in fact, I can go along and draw that vector in the x direction throughout the entire path that that ball has been launched, or whatever that thing was, projectile, okay? The velocity in the x direction stays the same. So the length of that line stays the same, and the magnitude, and the direction of it stays the same. I didn't have anything happen to it. What's happening to the velocity in the y direction, however? Well, I've got a negative acceleration, so I'm slowing down. So I am actually going to make that line look a little bit smaller. So there's the velocity in the y direction at b. And then what is the velocity in the y direction at c? Well, in this situation, that's where the maximum height is. And remember, there's the y and x directions are completely independent of one another. It's behaving just like an object that went straight up and down in the y direction. So the velocity of the y at the very, very top is equal to 0. Now I come to D, and because I'm accelerating downward, I now flip that vector because now I'm going negative. It's about, since it's the same location as B, it's going to be the same length of that line as B, except in the opposite direction. And then at E, it's going to be somewhere in the middle. And then finally at F, that y vector, that velocity in the y direction, will be the same magnitude. We'll call that final if we want. Actually doesn't matter, because we can pick and choose which is initial and final throughout the whole problem, as long as, we keep it that way while we solve that portion of it. Anyway, point is, that velocity vector at the end, at F, is exactly the same magnitude as it was at the beginning, except in the opposite direction. And why is that? Well, because the acceleration had a certain amount of time to slow it down to 0, and then had the exact same amount of time to speed it up again, because it's a parabola and it's symmetrical, okay? So this, if I solved for this, whoops, let's go back. If I use those two vectors at the very end and solve for this velocity, we'll call that velocity final, I will get the exact same velocity as I did in the beginning, except just at the 30 degrees below the horizon, okay? Because x is the same vector, y is the same vector, just opposite signs, okay? So now that was the velocity vectors. What about acceleration? Okay, we want to know about acceleration, so let's do that in purple. So let's do two acceleration vectors throughout the entire trip. Let's do y first. What's going on with y? Well, every single location, the acceleration in the y direction is negative g. That vector is always pointing downward. And it's the same magnitude on the way up as it is on the way down. Always and always, 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 always. There, it's in free fall, so it's 9.8 meters per second squared while we're on Earth in the downward direction. So no matter where I'm at, that vector is always pointing downward. Okay, not quite as clear. Okay, so that's the acceleration vector. Those lines are supposed to be identical in length. If they're not, that's because I'm artistically challenged. All right, what's going on in the y in the x direction? Let's use blue. Okay, well, it's 0. There is no vector in the x direction. Sorry, I said y, I meant x. There is no acceleration in the x direction the entire time, which is why the velocity in the x direction doesn't change. All right, now, I personally would love it if you stopped the video and asked all these questions of yourself in your notes and see if you would, what you get. But here we go. Pay attention to the words. When is the velocity 0? Some of you are going to answer, it's C. I didn't ask for the horizontal velocity. I didn't ask for the vertical velocity. I asked when the velocity was 0. That's the resultant vector. Never. I have a velocity at the entire time. When is the vertical velocity? Ah, now I have said the vertical velocity. Now, when is the vertical velocity 0? Is it ever 0? Yes, at C. When is the horizontal velocity 0? Never. When is the vertical, so straight up and down, acceleration 0? Never. Purple vector, it's always 9.8 pointing downward, meters per second squared. When is the horizontal acceleration 0? Always. Okay. What? Oh, this is good. This is going to get people. What is the speed of the object? I'm sorry. Let's see if I can read. When is the speed of the object the maximum? When is the speed? Did I say horizontal speed? Did I say vertical speed? No, I said speed. That is the resultant speed. There are two locations that have identical speed, which is the magnitude of the velocity. What are they? And they're both maximum. So the maximum speed occurs at A and F. Okay, so if I added those two X and Y components together and calculated that 30 meters per second, at no other time is that resultant vector as large as 30 meters per second. Why? Because the Y gets smaller and smaller and smaller and eventually becomes 0. And then the Y gets larger and larger and larger and then finally reaches the magnitude that it was before, just pointing downward. Okay, so that triangle's maximum value, that hypotenuse of that maximum value occurs at A and F. When is the speed of the object minimum? I didn't ask for horizontal. I didn't ask for vertical. When is the speed? So the whole thing. So add all those vectors up vectorially using your Pythagorean theorem. When is the speed 0? Well, when are the two vectors the smallest? The combination of the two? Well, the top. So at the top. Okay, that's the key to projectile motion, in my opinion, if you understand what's going on there. Okay, I have some more brain teasers. There's 1, 2, 3, 4, 5 of them. All right, here we go. 3 balls. Okay, 3 balls are launched horizontally. Okay, that's a very key word. Horizontally means it's only in the x direction. Initial velocity in the y direction 0. From a table such that the launch speed is The third ball has a higher launch speed than the second, than the third, or the first, okay? Determine the following. 3 balls are rolled off. Which ball will have the greatest range? That's in delta x. Well, what is delta x? It's equal to Vx times time, okay? Well, obviously the picture kind of tells you, we know this doesn't change, but what you may not realize is that the time that it requires to hit the ground is the same. And why is that? Well, let's take a look at each one of them. Every single one of these projectiles has an initial velocity in the y direction of 0. Every single one of these projectiles in the y direction has a negative g for acceleration. Every single one of these projectiles in the y direction, the displacement in the y direction, the height of the table is the same. Those are the 3 variables. If I want to know the time, I'm going to calculate the time for that ball 1, 2, and 3, and they will be the same, which is kind of weird. Therefore, I then come back to the only equation that works in the x direction. This time is the same, so V1 is less than V2 is less than V3, so therefore the one that has the greatest initial velocity in the x direction has the greatest range, which is ball 3. Okay, 3 balls are rolled off the same table at the same moment. Which ball will have the greatest hang time? Which one will have the greatest amount of time in the air? Didn't I just prove that they all have the same amount of time? They all have the same amount of time, okay? They're in the air. I know that seems weird, but in the y direction, everything is the same. My 5, 4, 3, 2, 1, I have 3 variables that I have proven, I know you know, that the initial velocity is 0, acceleration is negative g, delta y is the same because the height of the table is the same, all 3 of them. 3 balls are rolled off the table at the same moment. Which ball will have the greatest vertical speed? What is that? Vy, okay, which one is that? At the point of impact. Well, Vy initial is equal to 0. Acceleration in the y direction is negative g. They all have delta y is the same because they all have the same height. So if I find my final velocity in the y direction, which is what they said, greatest vertical speed at impact, vertical speed, I should have the same because all the variables are the same, all right? 3 balls are rolled off the table at the same moment. Which ball will have the greatest horizontal speed? So what are we talking about? We're talking about Vx final. Which one is the greatest? Well, acceleration in the x direction is 0. So what's happening to the so the only equation I have, see if I can write, that works for me in the x direction is delta x is equal to Vx times time. Notice I don't even have an initial or final. Why is that? Well, because acceleration is 0, so that means the velocity isn't changing. So which one has the greatest initial velocity? V3. So if V3 has the greatest initial, it's going to have the greatest final in the horizontal direction, which is x. All right, one more to go. 3 balls are rolled off the table at the same moment. Which ball will have the greatest speed? Okay. Did I ask for horizontal speed? Did I ask for vertical speed? No, I asked for speed. So that's the resultant vector. Don't forget, speed is just the magnitude of the velocity. The instantaneous speed is the magnitude of the instantaneous velocity because it didn't have time to wiggle and go in different directions, right? All right, so let's draw some vectors. I've got Vx, and I'm going to have a Vy at the very end, and this is what my resultant vector will look like. So there's my velocity at the very end, and so this is kind of like this area identified over here to the left. Okay, so let's think about it. This vector in the x direction, they told me that V3 had the greatest velocity in the x direction. Okay, so we know that V3 has the greatest x component. What about the Vy? Well, the Vy is the same for all of them because we proved that we have 3 variables. Delta y is the same. Acceleration is the same. Is this, okay, how about this? I'm getting tired, guys. Acceleration is the same, it's negative g, and we know that the initial velocity in the y direction was 0. So I have the three things and they're the same. So if I solved for the final velocity, it's the same. So therefore, the one that had the largest vector in the x direction, when combined vectorially with vy, which is the same for all of them, will result in the largest resultant vector, which will have the largest speed, which is the magnitude of the vector. Okay, that's what I got for you today. Come see me if you have any questions.